So now let's look at what led Isaac Newton to the concept of universal gravitation, and that was his attempts to try and understand the orbital motion of objects, particularly the moon, and how the moon moves in its circular path around the Earth. And ultimately, the way he made the connection that the gravitational force on the Earth was the same as the force that was holding the moon in orbit was by thinking about this. If, for example, we had a tall mountain and we placed a cannon on top of the mountain and we fired a cannonball, we'd find that the path of the cannonball would go something like this. It would follow that parabolic trajectory as gravity pulled it down. And if we fired the cannon even faster, then we would find that it fell something like this. And so Isaac Newton, sort of through mental exercise, thought, well, what if you were to fire the cannon fast enough? Wouldn't the cannonball simply follow a curvature which was exactly the same as the curvature of the Earth and come back up in the same spot? Now, in that condition, the object would continuously and endlessly go around in what we would refer to as orbital motion. And this is what the moon is doing. The moon is, in effect, falling. This cannonball is falling towards the Earth. But it just happens that the amount that it falls by is equal to the curvature of the Earth, so the distance between the Earth and the cannonball never gets any closer or further. And this is essentially what's happening with the moon. The distance between the moon and the Earth does change a little bit, but never gets close enough to actually come in contact with the Earth. And we probably should label that, so it'll be less confusing in the future. So this mental exercise led Isaac Newton to the concept of universal gravitation and the idea that two objects would be bound to each other as a result of the gravitational force. Who is causing the centripetal force? Well, in this case, the centripetal force is 100% the result of the gravitational force that's pulling the cannonball towards the center of the Earth. So this means that we can write the equation for centripetal acceleration, which is mv squared over r, and set that equal to, my mistake, g m1 m2 over r squared. Now let's think real quickly about which mass are we talking about here. When I talk about the centripetal force, I'm referring to the force acting on the cannonball, because the cannonball is the one who is continuously falling around the Earth. So he would be, if you remember, the convention is that the larger mass usually goes first. So in this calculation here, I would be using the mass of the Earth and the mass of the cannonball. So with mass of the Earth being 1 and cannonball being 2, that means over here, this is also mass 2, just like it was in our previous example when we calculated the gravitational acceleration at the surface. So we get some cancellation. m2 cancels out. The square comes off of the r, and we end up with an expression for the velocity of an object in orbit around a planet. And that expression turns out to be that the velocity squared is equal to the gravitational constant times the mass of the planet, or the object that's being orbited, divided by r. And they give an example, and let's pick an example, the example in the book. This is question 5 from page 139. And the question they ask on that page is, how fast does an object need to move in order to orbit at a distance of 500 kilometers above the surface of the Earth? 500 kilometers above the surface of the Earth. Well, in this case, we need to think carefully about the radius. They tell us that the radius of the Earth is 6.38 times 10 to the 6th meters. And we already know the mass of the Earth is 5.98 times 10 to the 24 kilograms. So I have everything that I need, but I need to think carefully about the radius. This question asks, what is the velocity of an object orbiting 500 kilometers above the surface of the Earth? So I need to add to this radius 500 kilometers. But now 500 kilometers is not the same thing as meters. So 500 kilometers would be approximately 500,000 meters. And so multiplying these two guys, or adding these two guys together, I should say, 6.38 times 10 to the 6th plus 500,000 gives me 6.88 times 10 to the 6th meters. So now I have the units, I have the radius, the distance between the center of the satellite and the center of the Earth. And one of the things that's sort of an interesting fallout of the way that the equations work is that you notice that the mass of the satellite doesn't matter. I could put you in orbit at 500 kilometers, I could put a car, a mountain, I can put any object that I want in orbit at 500 kilometers, and it will require the same velocity. All objects at that height will have to orbit at the same speed because it does not depend on the mass of the object who's going to do the orbiting. It only depends on the mass of the Earth. So we would calculate v squared to be 6.667 times 10 to the minus 11 times 5.98 times 10 to the 24. And now you have to be really careful because now we're not squaring the number on the bottom. Now the number on the bottom simply stays the way that it is. This is 88 times 10 to the 6th meters. And so we end up with a velocity of times 5.98 to the 24th divided by 6.88 to the 6th. So this gives me, so don't forget now, this is not the velocity. We need to square root the number to come up with the actual velocity. So I'm going to take the square root. And I end up with 7,612 meters per second. And of course there are 1,000 meters in 1 kilometer, so that means that we have a speed of approximately 7.612 kilometers per second. We're going to be looking at some very high speeds. Turns out that you have to move pretty fast, as you might imagine. I mean, if you throw an object, the object doesn't go into orbit around the Earth because it requires a tremendously high speed. 7.6 kilometers, so if we divide that by 1,000, that turns it into kilometers. And if we now divide that by 1.6, it turns it into miles. This is approximately equal to 4.75 miles per second. Miles per second. In terms of miles per hour, multiply that by 3,600. So the typical speed for an object orbiting at 500 kilometers above the surface of the Earth is about 17,127 miles per hour. So extremely fast speeds that we're going to be talking about. So you sort of have to get used to the idea that expressing things as meters per second, it's not always as convenient. We're oftentimes going to express things in terms of kilometers per second rather than meters per second. So make sure that you notice when you look at answers, you may see their answers are in kilometers per second or meters per second. You might have to make a conversion to get your answer to look like theirs. Now that's one way of looking at centripetal acceleration, and that's using mv squared over r. If you remember, there was another way of looking at centripetal acceleration, and that is the 4 pi squared r over t squared, right? And then I multiply that by the mass, and then that also would be equal to g m1 m2 over r squared. Now this leads to a little more complicated formula because notice the r's are not going to cancel now. And what would we be looking for here? Well, we would probably be looking for the period of orbit for that object. And let's figure out the period of orbit from the previous problem. Well, our first trick is, let's cancel out the masses, as they're not going to be relevant. And as a first step, let's go ahead and do some cross multiplication. So I'm going to end up with 4 pi squared r cubed equal to g m1 t squared. So then solving for t squared, I get t squared is equal to 4 pi squared r cubed over g m1 And that is a formula that I can use now to calculate the period of orbit for any object orbiting around another object. And as a minor side note, let me point out that t squared, now technically speaking, the mass is actually a variable. I could change the mass, but realistically the mass of planets doesn't really change very much. So the only thing that can really change is how far away you are from that planet, and then of course that correspondingly is going to affect the period. Now you would never expect, this is one of the most complex relationships we've ever seen. The square of the period is proportional to the cube of the radius. So let's write that down. T squared is proportional to r cubed. Now that's a fairly complex relationship. And this law is known as Keplers Third Law. This is how Isaac Newton knew that what he was doing was right. He knew that the gravitational force really was g m1 m2 over r squared, because when he applied it to the centripetal motion of the moon, he re-derived Kepler's third law. He actually figured out a way to prove that Kepler's law was true. Kepler came up with this idea that the period squared was proportional to the cube of the distance between the two objects, and he did not have any idea why it turned out to be that way. Isaac Newton went one step further and showed that Kepler's law was actually right, and it's based on the concept of universal gravitation and the natural laws of motion, the first, second, and third law. So let's use the example from back up in the previous problem, and let's calculate the period of motion for this object which is orbiting at 500 kilometers above the surface of the Earth. So we're going to continue on with question 5. Again, the radius in this case was 6.88 times 10 to the 6th meters. The mass of the Earth, 5.98 times 10 to the 24 kilograms. And so t squared will be equal to 4 pi squared, 6.88 times 10 to the 6th cubed divided by 6.667 times 10 to the minus 11 times 5.98 times 10 to the 24. So I have to tell you, this is where many of you will very frequently make a calculator mistake. So 4 pi squared times 6.88 times 10 to the 6th cubed divided by 6.667 e to the minus 11 equals divided by 5.98 to the 24th gives us, what does that give us? 32,247,000. But remember, that's not the period, that's the square of the period. So I still need to square root that answer, and I end up with a period of 5,678 seconds. Now we should convert that to hours. Well, let's convert it to minutes. That'll be easier. So there are 60 seconds in 1 minute. So if I divide by 60, I end up with 94 minutes. So satellites, and this represents the bulk of the satellites, are typically between 300 and 500 kilometers above the surface of the Earth, and those satellites go around every 94 minutes. This is the period of time it takes for them to make one orbit all the way around the Earth. And so we simply connected centripetal acceleration in two different ways, and of course we know there's a third way, which I won't do in the notes right now, but I could also have put 4 pi squared r f squared for frequency, and I could have calculated the frequency. Now it turns out that's going to be a pretty small number, because of course you know that the frequency is the inverse of the period. Well, 1 divided by 5,678 is a pretty small number, so the frequency is pretty low. It takes quite a while. But 94 minutes, that's not too bad to go all the way around the Earth in only an hour and a half.